This is the second part of the simulation lecture, and this time I'm going to show you how you can do type 1 error calculations and power calculations with logistic mixed effects models. The methodology is similar to the one that we used for continuous data for Gaussian likelihood, but the only difference is that the design R package is not able to replace the Gaussian likelihood with the logistic or the binomial likelihood. So we are going to write some code ourselves to use design R to create the basic structure of the experiment, so the basic data frame without the observed 0, 1 values, and then we're going to generate those 0, 1 values in by defining our own writing our own code. So the data I'll work with is from Grodner and Gibson, experiment 1, from a 2005 paper. And in that data we have already studied the reading time data quite a bit, but what we didn't ever, or maybe we looked at it, but we didn't really think too deeply about the 0-1 responses in the question response accuracies in the data. So what happened in this experiment was that readers read subject to object relatives in a Latin square setup, 42 subjects, 16 items, completely standard setting. And at the end of each sentence, they were asked a yes-no question about some dependency relationship within the sentence, and if the answer was correct, you record a 1, otherwise you record a 0. So we're going to use that data as a starting point for doing a power analysis and for doing type 1 error calculations. So first we'll fit the data using the G-Elmer function. So this is the function you need if you want to use the binomial likelihood, so the logistic mixed effects models. And everything else is the same, right? So we've got the 0, 1 dependent variable, question correct. We've got plus 0.5 minus 0.5 coded predictor, that's defined here. Varying intercepts and slopes with correlation for subjects, varying intercepts and slopes with correlation for items, and this is the data set. Okay, the only thing new is that we have a new family, and we don't use the Elmer function but the G-Elmer. G stands for generalized, so generalized linear mixed models. All right, so once you fit this model, what you get, as discussed in a previous lecture on logistic regression, what you get back is fixed effects and random effects, standard deviation estimates and correlation estimates, just like always, except that these fixed effect estimates are on the log odd scale, right? So I showed earlier how to convert back from the log odd scale using the plogis function, right? Okay, so we are going to first set up a design matrix, right, with the basic design that we are going to assume for the power analysis. So let's assume 40 subjects per condition. There are only 2 conditions, so 80 subjects. And so then the design object is created. See, you got fixed effect subject object with 2 levels, subject gap, object gap, plus random factor subject with 40 subjects per condition, random factor item with 8 items per condition. There were 16 items, as I said earlier. And and the subjects and items are the random factors, and the grouping is over the subject and object relatives factor. What that means is that we have repeated measurements both from subjects and for items for each of the levels of the factor FSO. So once you've defined the design object, you just run it through design.codes just like before, and you get your SIMDAT data frame, or tibble in this case. So this is the subject column with subjects labeled, item column with items labeled here, and then you've got the the factor FSO with the two levels, right? So they are, all three of these are factors. You can see that in the table output. So we can just double check that we have the right number of subjects, 80 subjects, 16 items. So the goal right now could be to find out what statistical power you would have if you were to run 80 participants instead of 42. Okay, so so just as a sanity check, just double check that the experiment has equal numbers of data points from each subject in the two condition levels. That happens to be true. This isn't the actual oh no, sorry, this isn't the simulated data, the data that we'll simulate. So in the SimDat object, we have a completely balanced setup, which is exactly the way the Grodin and Gibson experiment was too. They didn't have any missing data, right? Because it was self-paced reading. Self-paced reading, you can get data without any missingness, unless you explicitly make a move to remove some data, okay, which they didn't in this case. So now then we can just check that the subjects and items are crossed, right? So fully crossed would mean that each subject would see exactly one item, and that happens to be true. So I printed out the entire output for the 80 subjects, and you can see that this is true. There's not a single number other than 1 anywhere, right? So we're going to now take the FSO factor in the SimDat object and create a plus half minus half coding and put it in the vector SO. So now we are ready to generate some data. So we're going to add one more column that will contain zeros and ones this time instead of reading times or whatever, right? So first, let's extract the estimates from the fitted model. So this is the model we fit earlier with the G-Elmer function, extracting the intercept, the slope estimates, so the intercept and slope estimates, which are on the log odd scale, okay? And if you wanted to investigate type 1 error, you would set the slope to 0 because you'd be testing the proportion, you'll be trying to find out the proportion of cases where you get a significant result when the null is actually true, okay? But right now we are going to take the slope estimate as our estimate for the simulation. So we are studying power, okay? Now, the next thing I do is I will extract the subject random effects as a vector. So that's a vector. This is the intercept standard deviation estimate for subjects and the slope standard deviation estimate for subjects. And I've also extracted the correlation value, but what I did was I extracted it from the model by using this function called varchar for subjects, and what this returns is a correlation matrix, right? So if you remember chapter 1, we discussed all this in chapter 1. If you've forgotten, just go back and look at chapter 1 in the textbook. Look at bivariate and multivariate continuous distributions. Okay. So this is my the correlation matrix that I've extracted. And so on the diagonals, I've got ones. On the off diagonals, I've got the correlation between the intercept and slope. Okay. So just for illustration, right now, what I'm going to do is I'm just going to choose some intermediate value for the correlation. Let's say 0.5 instead of minus 0.37, right? So if I had set these values to be 0, then I'd assume that there's no correlation at all between the intercepts and slopes, right? And if it's minus 3.72, then that implies that increasing, what was the contrast coding? Yeah, object gaps are coded plus half. So increasing average reading time for a subject leads to shorter smaller differences between the object and the subject relative, right? So that's what that correlation would mean if that correlation were statistically significant. I don't know, I didn't check that, right? So just for illustration, I just changed it to plus 0.5. And then what I do is I build up the variance covariance matrix for subjects by doing the following. So first of all, I take the vector of standard deviations, right? I make it into a diagonal matrix. If you remember the diagonal matrix, if you give it a vector, so let me just try to do this. You know, if I have a vector like 1.2, oh sorry, 1.2 and 0.6 or something like this vector, if I run it through the diagonal function diag, what I will get is a diagonal matrix with those two numbers along the diagonals, and the off diagonals will be 0. Okay? So that's what I did here for the standard deviations of the subject random effects. Then I matrix multiplied that with the correlation matrix, which is this guy here. So this is 2 by 2, this is 2 by 2. You multiply this, you get a 2 by 2 matrix. And then I multiply that again with the diagonal random effects matrix for subjects, right? I'm doing this because if you remember in chapter 1, well, if you don't remember, just go and look at the chapter. But basically the way you assemble a variance covariance matrix, one way that you can assemble a variance covariance matrix is pre-multiplying and post-multiplying the correlation matrix with the diagonal matrix containing the standard deviations, right? And what that will do is that it will put the variances, not the standard deviations, the variances along the diagonals and the covariances along the off diagonals. So the details are all in chapter 1, so I won't repeat anything here. You can look at that yourself. All right, so same thing for items now. I just created the variance covariance matrix for subjects. Okay, now I'm going to create one for items. So there's the item random effects standard deviations. I extract those. Then so those are the standard deviation estimates. Then I create sigma w, which is the yeah. So what I'm doing here is that I just took the diagonal, created the diagonal matrix for the item standard deviations, and I just squared all the standard deviations. So what that does is it puts the variances on the diagonals and it leaves 0 on the off diagonals, right? So I'm assuming no correlation between intercepts and slopes and subjects in items. Sorry. So the reason I'm doing that is that I have only 16 items. It's going to be virtually impossible to get a reasonable estimate anyway of the correlation, so I just assume no correlation. And anyway, the standard deviations are much smaller in the items than in the random effects for subjects. So okay, so here I was just checking the eigenvalues. You can ignore this, okay? This was just me checking something, so we won't talk about that right now. And now we're going to run 100 simulations, and in each simulation we're going to do the following. We're going to create the random effects for subjects and for items. So what this means is if I have 80 subjects, for subjects, when I say random effects matrix, what I mean is I'm going to create a matrix of 80 rows and 2 columns. 80 rows because there are 80 subjects, and 2 columns because I've got varying intercepts for each of the 80 subjects and varying slopes for each of the 80 subjects. I'm going to do the same thing for items as well, except it will have 16 rows. Okay, so that's what I mean when I say create the random effects matrix for subjects. I will do this in each simulation afresh to simulate new subjects each time. Okay? And so for each row in the data frame, that is the SimDat data frame, I'm going to generate predicted values on the log odd scale, and I'm going to generate predicted values on the log odd scale. And then for each row in the data frame, having created those predicted values in the simulation on the log odd scale, I will convert those log odds back to probability scale and then generate a 0 or 1 from a Bernoulli distribution or a binomial distribution with number of trials equal to 1. Okay, so let's see how this works. 100 simulations, 80 subjects, 16 items. This is the number of rows in my simulated, in my simulation data frame, which contains no dependent variable. So that would be 80 times 16 because each subject is seeing 16 items. Okay, so this would be 80 times 16. All right, so oops. So we're going to just rename the columns for subjects and items as numerical values. I just did this in a very stupid way, but you can probably do this better than me. You people are highly trained by now. So all I did was, instead of writing subject O1, subject O2, I'm just going to have numbers 1, 2, 3, 4. And instead of having item O1, item O2, I'm going to have 1, 2, 3, 4, etc. Okay, that's all I did here. And so if I look here, what do I get? I get a subject column. Oh, here, like I've got a subject column, numerical values now, and an item column, and I have my contrast coding. And basically this is all the information I need. These 3 columns is the critical information that I need to simulate data now. So that's why I will isolate those columns and use those for generating data. Okay, so let's go. So the way we are going to generate the data, we're going to be writing 2 for loops now. Okay, so first of all, I'm going to write one for loop, the outer for loop, which will run 100 times. Each time there'll be a new data set generated in that for loop. Okay, so the way I will do that is, first I will generate the random effects matrix for subjects. So remember that U is now 80 times 2 matrix. Then I will generate a random effects matrix for items. That will be a 16 times 2 matrix. This will be done each of the 100 times. Okay, so this is iteration 1. And here I've just generated my subject random effects. Okay, so what this assumes is that some subjects are slower than average, some are faster than average, and some have larger than average effects, some have smaller than average effects. Same thing for items. Okay, then I'm going to create a Q correct vector that has as many empty cells as there are rows in the data frame, which is 80 times 16. Okay, and then once I've set this up, what I'm going to do is I'm going to start a new for loop that runs through the SIMDAT data frame one by one, row by row. Okay, so 80 times 16 times. Okay, that's 80 times 16. I'm going to run another for loop inside the for loop that will do the following. First of all, I have already estimated the beta 0 and beta 1 values, right, from the fitted model, from the Grodin and Gibson data. I also have the U matrix, the subject random effects matrix, and the item random effects matrix. And the first column of the subject random effects matrix, the first column of the item random effects matrix contains the intercept adjustments, right? So what I'm doing here, to concentrate your mind on this now, okay? What I'm doing in that highlighted region is that I'm looking at the 80 times 2 U matrix, the subject random effects matrix, and what I'm asking is, what is the number that is in the first column that corresponds to the subject ID of the SIMDAT data frame in the ith row? Okay, remember this I is indexing the row in the data frame. So for any row in the data frame, if I extract the subject ID for that row, this long command here will be replaced with a number that ranges from 1 to 80, right? It could be 1, 2, 3, or 80 at most, because there are 80 IDs here. So what that does is that if I get, let's say I get the number 1 here, which tells me that the matrix, the subject's random effects matrix in the first row and first column, first column, what I have is the intercept adjustment for subject 1. Similarly, if I were 2, then I would look at the subject random effects matrix, look at the second row. I would be 2, so I'll be looking at the second row, and I would extract the subject ID in the second row. It could be subject 2, for example, right? So this command tells me, as we walk through the data frame SIMDAT, which subject ID we are looking at, and this tells me the relevant subject intercept adjustment for that subject ID. Okay, so if you understand this command here, then you'll understand the rest of the formula here as well, because I'm doing the same thing for items, except instead of subjects, I'm looking for the item ID. And then for the slopes, I'm looking at not the first column in the U subject random effects matrix, but the second column. Similarly for items, I'm looking in the second column now. Okay, so this gives me the fixed effect estimate plus the subject and item adjustments added on to the fixed effects estimate for every row in the data frame, and I'm going to multiply that with the SO value in the ith row. Okay, so that this is generating a predicted log odds value for every row in the data frame. So I'm calling it mu hat. Okay, I'll just call it mu hat. And then what I'm going to do is I'm going to take that the sum of all those terms saved as mu hat. Remember, this is going to be done for every row in the data frame. Okay, so 80 times 16 times. So once I've saved mu hat for the ith row, I'm going to plug it into this equation, because this is the equation for the p-logis function, right? If you remember the logistic regression stuff. Once I have the log odds, and I have the log odds for the ith row, I can convert it back to probability for that row. This is the probability for that particular row in the data frame, okay? The probability of getting a 1 or a 0. So now that I have a single number, which is the probability going from for the particular row in the data frame, then I will run it through the binomial R binom function with n equal to 1. I mean, I could have used a Bernoulli, right? R Bern, but I'm just using R binom. I'm generating one data point, which will be either a 1 or a 0, because n is equal to 1, with probability equal to whatever I generated just now from this equation here. Okay, but I back transformed the log odds for the ith row into probability and use that to generate a 1 or 0 probabilistically. Okay, so what will happen is in the ith row of the Q correct vector, which I had created earlier, remember, in the outer part of this loop, in the first for loop, I created a vector with n cells. So I'm going to put into the ith row of that vector the corresponding 1 or 0 value that will be generated. Okay, so that's the end of one data generation. Once I've run through this inner for loop, this inner for loop gets me through, creates one full data set for me, and I do that 100 times. That's why you got an outer for loop, and each time that we start the outer for loop, we generate new intercept and slope adjustments for subjects and for items. Okay, so once the one data generation process finishes, I've got a SIMDAT object with QCorrect as a new column in it. So if you remember the SIMDAT object that we had, it did not have any data. So we've added the QCorrect column here now, okay, after generating those data points. So once we do that, we can fit the G-Elmer function with the binomial family. Same command as earlier, but notice that I'm assuming no correlation between intercepts and slopes for items for the reasons I explained earlier. So in any case, I run the function, I fit the model, I save the model with my, this is simulated data, so that's why I'm calling it fake. So I've got a fitted model on the fake data, and I'm extracting the second row, third column, which is the t value for the slope, or rather the z value or the z value for the slope, and I'm saving it in this vector called zval, which was created at the very beginning here, also before the first for loop started, the outer for loop started. So now I've got, once this outer for loop finishes, the outer for loop finishes here. That means I've generated 100 data sets each time, and each of those 100 times I figured out whether the Z score or the Z score was what the Z score or Z score was. Okay, I keep saying Z score or Z score because the Americans say Z score and the British say Z score, and like it's a mess. Anyway, so then what I do is, once the outer for loop finishes, if I'm trying to compute power, what I'm going to do is I'm going to get the absolute Z value or Z value and figure out what the proportion of values is, that is absolute values is that's larger than 2. That means that I have a statistical power of 12% in this experiment with 80 subjects and 16 items. So the point is that, let's say I'm trying to find out if there's a significant difference in question response accuracy between subject and object relatives in English in the Grodner and Gibson design using their items, but with new subjects, how many subjects would I need to detect that difference, right? And assuming that the differences that were the effects estimates that were reported by Grodner and Gibson's that were reported or that were estimated from the Grodner and Gibson data, because we estimated them ourselves. We are not looking at the reported values because, as far as I remember, they didn't fit a linear mixed model. This is 2005. I think the Elmer function didn't even exist then, right? So they were doing paired t-tests or ANOVA or something. So we reanalyzed the data. Ted Gibson gave it to me very kindly, and then once we reanalyze the data, given the estimates in that data set of the intercept and slope and the variance components, if those reflect the true values, of course that's a very big if, okay? If those reflect the true values of the parameters, then our power is 12%. So we would need a lot more than 80 subjects actually. So basically that's it. So there's some variations that you can now, of course, do. For example, there are some decision points that you have to think about, in practical data analysis. And the decision points are these here, right? Deciding on the variance covariance matrix for the items and for the subjects, right? So I took some arbitrary decisions just to illustrate how to do this. But in your real life setting, you'll have to decide how complex a variance covariance matrix you want to assume here, okay? But it's not a big deal. I mean, you'll quickly get the hang of it once you do it a couple of times, right? So now what I want in the class, I will ask you to do some exercises with different effect sizes, different subject sample sizes, and I will also ask you to rerun that same set of simulations, different sample sizes, with an effect size set to 0. So we will want to know what type 1 error is, and we will do that for two kinds of models. One model which will be only varying intercepts, and another model that has varying intercepts and slopes. And what you're going to find in the class exercise is that if you fit an overly simple model, varying intercepts only, in this kind of setting, your type 1 error is going to go up dramatically. It's going to go up to 0.15 or something crazy like that. So instead of 0.05. So that's basically it. It's a very straightforward extension of the power and type 1 error simulation that we saw for continuous data. You just change the likelihood function, here to the binomial. The only complication is the use of the log odds scale, which we have to back transform from to the probability scale in order to generate data from a binomial or Bernoulli distribution for each row in the data frame. That's the only complication, nothing else. Okay. So that's it. And so I think we are done with this course. Congratulations.